Episode 3, Radicals and Rational Exponents. Today we're going to talk about radicals, that is roots, and then how we can write those as in an exponential form if we use rational numbers as exponents. Right, so let's review here a little bit, right? The square root, right, you know what the symbol means here, right? So if we let a be greater than or equal to 0, then the square root of a is denoted with this thing called the radical sign over a, right? It's the non-negative number such that when you square it, you get a, right? So the square root of a times the square root of a is a, right? And then the nth root, here I'm thinking n is greater than 2, so greater than or equal to 3 in an integer. Right? The notation is the same as the square root, except to the upper left there we have the n put in there. Right? We don't put a 2 for the square root, but for other roots we put the power there. Right? It's the number such that when we take the nth root of a to the nth power, we get a. We have to be a little bit careful here. If a is greater than or equal to 0, then the nth root of a is also greater than or equal to 0. If a is negative, we have to be careful about this. If a is negative, the nth root of a is only defined if n is odd, and in that case, the nth root of a is also negative. We will talk more about this in just a second. Now, for any power of n, the nth root of 0 is defined and it is equal to 0. Right? The square root of 0 is 0 because 0 squared is 0. Right? No problems there at all with 0. Right? Any root of 0 is 0. Please remember that. Don't worry about taking the square root of 0. Square root of negative numbers, yes, problem, but not 0. So let's talk a little bit more about odd roots versus even roots. We'll start with odd roots. Right? If n is odd and greater than or equal to 3, then x equals the nth root of a is defined for any a, right? And it's the only real number that satisfies x to the n equals a. I plug x equals nth root of a into that equation, take it to the nth power, it cancels out that root, and we're left with a. If a is positive, the nth root of a is positive. If a is negative, the nth root of a is negative. We have no trouble. Now, it's even roots where we have some trouble, right? If n is an even positive integer, then x equals the nth root of a is only defined if a is greater than or equal to 0. But there's another aspect to that. There are going to be two different real numbers that satisfy x to the n minus a equals 0, right? Or x to the n equals a. That's going to be x equal the nth root of a. That will be a positive number. And then x equals minus nth root of a. Why? Well, if you multiply a negative number times a negative number, you get a positive number. And so if you're multiplying things together an even number of times, there's no way for that thing to be negative because you'll always be able to pair up those negative signs. Or the root can't be positive, right? Because a positive number times itself, how many ever times, is going to be positive as well, right? So we cannot take the even root of a negative number. We can take the odd root of any real number. Okay, some examples here, right? We can simplify this sometimes, right? The square root of 9. 9 is 3 times 3, so that would be 3, right? So the square root of 9 is equal to 3. Please don't confuse that with plus or minus 3. That is the thing that is important to know, but it has a different context, right? Square root of 9 is a single number that is positive. Plus or minus square root of 9, or plus or minus 3, is important in the context of solving the equation x squared equals 9. So that, because plus 3 and minus 3, if we square both of them, we get 9. So that as an equation has two solutions. But that's not what I'm talking about here. I just want to know What's the square root of 9? The square root of 9 is going to be the single number 3. So it's kind of subtle there, right? It depends on whether or not you're really solving an equation. Here, we're not solving an equation. We're just square rooting a number. The fourth root of 16, right? I want the number that if I multiply together 4 times, I get 16. That's 2, right? 2 times 2 is 4, so 2 times 2 times 2 times 2 would be 4 times 4, or 16. The fourth root of negative 16, well, that's a problem, right? 16 is a negative number, and so we can't, and 4 is even, and so we can't take the even root of a negative number, so that thing doesn't exist. But the fifth root of negative 32, no problems there, right? 5 is odd, and so negative 2 times negative 2 times negative 2 times negative 2 times negative 2, right? Those cancel. Some of those negative signs cancel, but we're left with 1 left over, and so the fifth root of negative 32 is negative 2. Now, one thing to be careful about here, what is the square root of x squared? It is not really x, right? We can't, based on this alone, we cannot conclude that it is x, right? As an example, what's the square root of negative 5 squared? Well, negative 5 squared, if we think about this, right, that is 25, and the square root of 25 is 5, not negative 5, right? This is really the definition of the absolute value, right? The absolute value of x, denoted with those 2 bars, right? It's the non-negative number that's the distance x is away from 0, right? That's really its best definition, but you can think of it as precisely this, right? You plug a negative number into the absolute value of x, it's going to give you a positive number out. And it does that by squaring it and then taking the square root of the positive number that you get after you square it. There's a different way to think about it that is also very useful. If x is positive or equal to 0, then the absolute value of x is x. If x is negative, well, then you just multiply by -1 and you get a positive number, as the absolute value needs to be. It is really helpful to understand this piecewise definition. We'll talk about that a little bit more later. It certainly shows up in calculus, so kind of file that away for use later. Okay. Now, we'll spend the rest of the time thinking about the connection here to rational exponents. So let's let n be greater than or equal to 2 and be a positive integer. And if n is even, we'll let, that should be x be greater than or equal to 0. Then x to the 1 over n power is equal to the nth root of x. That's how we can represent this radical in terms of a rational exponent. For more general rational numbers, p over q, x to the p over q power is the qth root of x to the p, or we could also think of that as the qth root of x raised to the p power. The order that we do those in doesn't really matter. Why is this the case? It comes from one of the laws of the exponents that we looked at last time, right? We wrote it as a to the m to the n power was a to the m times n power. If we let m equal 1 over n, well then 1 over n times n, right, those cancel, that's 1. So x to the 1 over n power has to be the number that when you raise it to the nth power, you get x, right? So that's why this has to be true, right? So x to the p over q power, it's the qth root of x to the p, or the qth root of x to the p power. The order we do those in doesn't matter, right? So let's do some examples here. Rewrite the following expressions with rational exponents in a radical form, and then simplify as appropriate, right? So what does x to the 2/3 power mean, right? That's x to a rational number, right? That's going to be the cube root of x squared. Now, what about x to the 3/2 power, right? Well, right, that's going to be the square root of x cubed, right? Now, let's be careful here. N equals 2, right? The bottom is even. So we are implicitly assuming here that x is greater than or equal to 0. So that's where this thing is defined. But I can also think about, right, 3/2, that's 1 plus 1/2. So I can think of this x to the 3/2 power as x times x to the 1/2 power. X to the 1/2 power would be the square root of x. So I can think of this as x times I can think of this as the square root of x cubed, but I could also think of it as x times the square root of x, right? Which I think about getting from a couple of different ways, right? X to the negative 5/6 power, right? It's a negative thing, so we would have 1 over x to the 5/6 power. Right, so that would be 1 over the 6th root of x to the 5th. Here we're assuming that x is greater than 0 because we can't take the 6th root of a negative number, and then we also can't divide by 0. So the negative numbers and 0 are removed here, but for different reasons. And then one other here, 8 to the 4/3 power. Right, if you think about that, I could write that as the cube root of 8 to the 4th power, but I'm going to do that in a different way, right? It's much easier to think about this as the cube root of 8 to the 4th power, because the cube root of 8 I know is 2, and so this is just 2 to the 4th power, which is 16. It's a lot simpler than trying to think about the cube root of 8 to the 4th power, which is 4,096. I don't know off the top of my head what the cube root of 4,096 is, right? But I do know what the cube root of 8 is. So when you're evaluating something like this for a specific number, it's usually easier to think about taking the root first and then raising it to the power. Or I could do something like I did up at number 2. X to the 4/3 power would be x times the cube root of x. So I could do it that way as well. Now let's think about these expressions that have radicals in them and go the other way to exponential expressions and simplify them. So the 10th root of x, well, that would be x to the 1/10 power. The 8th root of x to the 7th, that's going to be x to the 7/8 power. The 4th root of 100, 100 is 10 squared, right? So this would be really 10 to the 2/4 power, right? So that would be 10 to the 1/2 power, or the square root of 10. Now let's think about some expressions here with radicals, and I want to write them as x raised to a single power, right? So I have the square root of x times the cube root of x. Right, well that's going to be x to the 1/2 plus 1/3 power. So that would be x to the 5/6 power, right? I get my common denominator of 6. I get 3/6 plus 2/6, I get 5/6, right? And then here I've got x cubed times the square root of x divided by the 5th root of x cubed, right? So here, right, all those bases are the same. All those bases are the same. So I'm going to write this as x to the power 3 plus 1/2. The plus 1/2 is for the square root of x. And then minus 3/5. So that's, right, that's the 5th root of x cubed in the bottom, which is where the minus sign comes from, right? So I have 3 plus 1/2 minus 3/5. Right, so I get a common denominator of 10, add those up, and I get x to the 29/10 power. So that'd be the 10th root of x to the 29th power. And then one more here, I have x to the 2/3 power raised to the negative 1/4 power. So that'll be x to the power of 2/3 times negative 1/4. So that's x to the -1/6 power. Right? My laws of exponents say I have a base to a power to a power. I just multiply the powers together, and then I need to think about what I get when I multiply those fractions together. All right. One more concept here before we close, the idea of rationalizing the denominator. Right? It's common to expect an irrational number expressed as a fraction where the denominator contains no radical expressions. So the denominator is an integer, even though the top may not be. The idea here is if we have an expression where the denominator does have a radical in the bottom, we want to be able to find an equivalent expression for that number that doesn't. This is called rationalizing the denominator. We do that by multiplying by 1. We just call 1 something a little bit different. This is not something that I require that you do, but it is something that I need you to know how to do because the technique of doing it becomes important for a couple of other things, right? Let's do an example here, right? 3 divided by the square root of 5. Square root of 5 is not an integer, right? So we need to figure out some way to get around that. I need to multiply by something that will turn that square root of 5 into an integer, but yet still keep this as the same number. So I need to multiply by 1. I can just call that 1 square root of 5 divided by square root of 5, right? Square root of 5 over square root of 5 is 1. But if you look at what that's done, square root of 5 times square root of 5 is 5, right? And so I have my integer in the bottom, right? So 3 over the square root of 5 is equal to 3 square root of 5 divided by 5. Now, why is that considered better? If there's something in the homework where this is the answer, unless I'm specifically asking you to rationalize the denominator, this is a perfectly acceptable number. Why have your previous teachers insisted that you must write it as 3 square root of 5 over 5? It actually goes back to the days before we had pocket calculators, or the ones you have on your phone, right? If I needed a decimal representation of this number, I would walk over to the shelf, grab a book, and look up the square root of 5. Someone who wrote that book did a lot of work by hand to get an approximate value of that as a decimal. And then I would need to do long division to get the number that I want, right? And it's hard to do the long division by hand of 3 divided by 2 point whatever that square root of 5 is, right? But it's much easier to multiply 3 times that number and then divide it by 5 if you're doing it by hand. We don't do a lot of that by hand these days, right? And so this expression is really not that bad, right? But you do need to know how to convert it to that for other things that will come up later. Right, so let's do the second example here. 6 divided by the cube root of 2. Now this is a little bit different here. I need the thing in the bottom that when I multiply the cube root of 2 by it, I get an integer. Now that's not the cube root of 2. Cube root of 2 times cube root of 2 would be the cube root of 4. No, I need to multiply by the cube root of 2 squared, right? So that I get 3 cube roots of 2 multiplied together to get me 2. Right? So that's the cube root of 4. So this would be 6 cube root of 4. The 6 divided by 2 is 3. Right? And then one more here. Square root of 5, the square root of 5/7. I can think of that as the square root of 5 divided by the square root of 7. And so I just multiply it by square root of 7 over square root of 7. So that's going to be the square root of 35 divided by 7. So I've rationalized the denominator there, right? It's important to know how to do this, but again, I would gladly accept square root of 5/7 as a perfectly valid answer on a test or something.